Our main example of an application for second-order linear differential equations will be describing what's called harmonic motion. And one very physically accessible way of generating harmonic motion is by hanging a mass from a spring. So that's what we're going to look at first. So classically speaking, to model a mass hanging from a spring, we're going to assume that our spring obeys what's called Hooke's law. And Hooke's law says that the force exerted by a spring is proportional to the displacement of that spring from its so-called natural length, its sort of resting position. So y is the coordinate that describes the position of the mass. So y equals 0 is at the natural length of the spring. K is the constant of proportionality that just tells you how strong the spring is. So the larger K, the stiffer the spring. The units for K usually comes in force units, so newtons per distance unit, so that would be per meter. Right, so if K is larger, that means it's exerting more newtons for every meter that you stretch the spring. This minus sign here, just in Hooke's law, just says that the force the spring exerts pushes in the opposite way that you stretch the spring. In other words, it pushes the spring back to its natural length. So in this situation, we actually have all the tools that we need to write down a differential equation for this sort of system. So if we have a mass with 2 kilograms and a spring whose spring constant is 4 newtons per meter, we can write down a differential equation for this system. So go ahead and pause this video and work on the first couple problems. And if you get stuck or need some help, you can unpause the video. Okay, so let's work on number 1 here. So we're going to try to write a differential equation to describe the mass on the spring. Now we are assuming that we're in some situation where there's no gravity, so say deep in outer space, so we don't have to worry about how the gravity acting on the mass changes the situation. In fact, it doesn't change the situation, which we'll look at later, but just to make things simple, let's assume we have no gravity. So Newton's second law says that the sum of all of the forces is equal to the mass times the acceleration. And acceleration, since our object is just moving in one direction, acceleration is just going to be the second derivative of y. The net force, well, in general, you add up all of the forces, but in this situation, there is only one force acting on the mass, and that's the force of the spring. So this is just going to be our spring force. Okay, so when we write this down, our spring force is minus ky, and that is supposed to be equal to the mass times acceleration, and acceleration is y double prime. And if we rearrange this, we get mass times y double prime plus ky equals 0. Okay, now let's take stock of what kind of equation this is. Well, it's a second-order differential equation, right? There's 2 derivatives of y here. It's also constant coefficient because the mass isn't gaining or losing any material, so the mass is constant. And we've assumed that this spring is well behaved, so its spring constant is actually a constant. So this is a constant coefficient second order homogeneous linear differential equation. It's our favorite kind of differential equation. So if we put in the constants that we have, we get 2y double prime plus 4y equals 0. Now, since this is a constant coefficient differential equation, if we think about uniqueness of solutions, well, remember, we get uniqueness of solutions when these coefficient functions are constant and this leading coefficient function is non-zero. But since they're these coefficient functions need to be continuous and the leading coefficient non-zero. But since they're non-zero constants, these coefficient functions are always continuous and the leading coefficient function is never 0. And so we always get unique solutions for every initial condition. That kind of makes sense intuitively it makes an intuitive physical sense because an initial condition is just an experimental setup, right? An initial condition would be at an initial position for the mass and an initial velocity for the mass. And if you position this mass at some position and then throw it at some velocity, you should get one single possible behavior. And that is indeed what the uniqueness theorem tells us. For a particular physical setup, you get a unique behavior. So it's kind of comforting that that works out. Okay, so now that we have a differential equation, we could actually solve it to see what the behavior of this situation is. So go ahead and pause the video and work on part B, solving this differential equation. Okay, so let's solve this differential equation. Now, since this is a constant coefficient homogeneous linear differential equation, we can just use our characteristic equation trick to find solutions. So first of all, we can divide both sides by 2, I guess. So y double prime plus 2y equals 0. The characteristic equation is going to be m squared plus 2 equals 0. So m is going to be plus or minus the square root of 2 times I. And so our solutions are going to be, let's see, the first one. So the imaginary case is where you get sines and cosines. So we get sine root 2 times t. And the second solution, or the second linearly independent solution in our fundamental set, is cosine root 2 times t. Okay, so in general, our solution is going to look like y is some constant times sine root 2t plus some other constant times cosine root 2 times t. All right, now we have some initial conditions, so we can go ahead and apply those initial conditions. So y of 0 is 0, but if we plug 0 into our general solution down here, we get c2 times cosine of 0, right? Sine of 0 is 0, so the sine part goes away. So that means y of 0 is supposed to be 3, not 0. So c2 is 3. And then we need a derivative to use our other initial condition here. So y prime is root 2 times c1 cosine root 2t minus c2, which we now know is 3, times root 2 sine root 2t. And now we can use our initial condition. So 0 is y prime of 0. And plugging 0 into this, we get, let's see, root 2 times c1. And so c1 has to be 0. So our solution for this particular initial condition is, looks like it's 3 times cosine of root 2t. All right, so we solved this, this initial value problem. So go ahead and pause the video and work on the next couple problems on your own. Okay, so let's have a look at 2. So this is basically the same situation as our first example, except we have general constants instead of actual values. Okay, so we had, the general setup was mass times acceleration, which is y double prime, has to be equal to the force, which is minus k times y. We can move the minus ky to the left, so we get m times y double prime plus ky equals 0. And just like in our concrete case where we had actual numbers to deal with, these coefficient functions are they're continuous everywhere because they're constants, and the leading coefficient function, the mass, is non-zero. So this differential equation will have unique solutions for every initial condition, which is great. Again, that sort of corresponds to the fact that if you set up the physical system, it has a unique behavior. All right, so go ahead and pause the video and look at part B. Okay, so actually solving this equation, well, it's still a second order constant coefficient homogeneous linear differential equation, so we can play exactly the same game as before. Divide both sides by m just to get that y double prime by itself, so y double prime plus k over m times y equals 0, and then we can write our characteristic equation, m squared plus I guess it's sort of unfortunate that we use m in our characteristic equation. Just for this example, why don't we use r instead of m? So r squared plus k over m times y. I'm sorry, not times y. So here's our characteristic equation, r squared plus k over m equals 0. Solve for r. We get r is plus or minus the square root of k over m times I. So we're still in this pure imaginary case in our characteristic equation. So our solutions are sine square root k over m times t and cosine square root k over m times t. And so the general solution is just a linear combination of these. So C1 times the sine plus C2 times the cosine. Okay, and you can see that because this is built out of sines and cosines that have the same angular speed here, no matter what the constants C1 and C2 are, this function is going to have, have a period. So this is a periodic function. And in fact, this linear combination of sine and cosine with the same angular speed is just a shifted sinusoid. And so this, no matter what your initial conditions are, this will just oscillate back and forth as we expect. So that's good. All right, have a go at the next problem on your own. Okay, so we do have periodic motion. So what is the period? Well, the period for sine and cosine is 2 pi, and the general relationship between this angular speed here, so usually the letter we use for angular speed is omega, so I'm going to say omega is the square root of k over m. This is, so angular speed, sometimes this is, some people call this the natural frequency, but that term is a little misleading because it's actually not a frequency. So maybe it should be called the natural speed or natural angular speed of the system. So the relationship between this angular speed omega and the period of this oscillation is that the period is 2 pi over omega. Okay. You can see that this kind of makes sense because if omega is 1, then we're just dealing with bare sine and cosine, and the period is indeed 2 pi. If you make this larger, then it will take less time. A larger angular speed means this will take less time to go through one oscillation, and indeed, if you make omega in this fraction larger, it makes this whole fraction smaller. So a larger angular speed gives you a smaller period. So that makes sense. So in general, the period is going to be 2 pi over square root k over m. So that's 2 pi times the square root of m over k. All right, have a look at the next one by yourself. Okay, so for the effect of increasing or decreasing the mass and the spring constant, we can just use this expression that we found for the period. The period is 2 pi times the square root of m over k. And omega is the square root of k over m. So let's imagine that we increase the mass, which is m. So intuitively, if you increase the mass without changing the spring, more mass means it's harder for the spring to push the mass around. And that means that everything should happen slower. So just based on an intuition, if we increase the mass, the period should increase, and that means the angular speed should decrease. So now let's use these formulas and see if that's what actually happens. So if you increase the mass, the denominator in our omega is getting bigger, and that means this whole fraction is getting smaller. So this checks out. And for the period, if you increase the mass, that in the period, the mass is in the numerator, and so this fraction gets bigger. And so if you increase the mass, the period gets bigger. And yes, that checks out. Now let's, of course, if you decrease the mass, the opposite happens. Now let's think about what happens if you increase the spring constant k. So remember, k measures how stiff the spring is. So if you make the spring stiffer, it's generating more force, and so it ought to have an easier time pushing the mass around. So everything should happen faster. So we sort of suspect that the period should decrease and the angular speed should increase. And indeed, that is what happens. Since k is in the numerator for omega, when you increase k, omega increases. And since k is in the denominator for the period, when you increase k, the period decreases. So both of these check out as well. Of course, if you weaken your spring by decreasing k, the opposite happens. The period gets bigger and the angular speed gets larger. I'm sorry, smaller.